Welcome to the next video for finding the area between curves. Now, before we used to find the area underneath a curve using Riemann sums, and we broke them into rectangles and to find the area of those rectangles, and then we added them together. So we're going to use the same sort of idea for the main concept of this idea today. So let's look at example 1. We've been given two graphs. One of them is x squared plus 1, and the other one is x. For A, we want to show the LREM approximation of the area underneath the curve of x squared plus 1. And we're going to have 4 rectangles. So our very left point in each interval, and we need 4 of them. So I'm going to go from 0, 0.5. I'm going to write in those in between increments because we're going to go from 0 to 0.5 to 0.5 to 1 to 1 to 1.5 and then 1.5 to 2. This will give us 4 rectangles. And in between these intervals, I'm always going to pick the most left point. So in between 0 and 0.5, I'm taking this point here that touches the graph to create my rectangle. Then for 0.5 to 1, I'll take my most left point, which is at 0.5, and use that to create my rectangle. From 1 to 1.5, I'll choose 2 to create my next rectangle. And our last one, we have a point here at 3.25, and this will give us our last rectangle. So that's what our LREM looks like in terms of pictures. Now we're going to do the same sort of thing for y equals x. The same increments because I still want 4 rectangles. I'm going to pick my most left point. So between 0 and 0.5, my most left point is just 0. So we don't really have a rectangle there. From 0.5, I have 0.5 for my y, and that creates our second rectangle. Then the most left point between 1 and 1.5 is 1. And then lastly, at 1.5, I have a point at 1.5. This will create the last rectangle. So if you're looking at the area between these two, well, I'm going to redraw what I just drew. I'll draw all the rectangles from x squared plus 1. I'll use a different color to show the Riemann sum, left-hand Riemann sum for y equals x. So here I just combined A and B onto one graph. So if we want to find the area between those two curves, then we're going to end up with just this, what's in between them. So what we're going to actually do then, we need to subtract the B, or we need to subtract A from B to get C. So this is the area between curves, which is calculated as B and A, but subtracted from each other. And we'll be left with whatever is left over. Now if we go away from the LREM and think about in terms of integrals, if I want to find the area underneath x squared plus 1, then the interval will be from 0 to 2 because that is the interval of x squared plus 1 dx. For B, same bounds from 0 to 2, but my function now is x and dx. So if I want to find the area between them, I would just take these two integrals and subtract them. Which is the following under one integral. Okay, so in other words, this is the formula we're going to use. the area between two curves is going to be the interval from a to b of f of x minus g of x dx, where g of x is smaller than f of x. So usually it'll be integrate the top minus the bottom. So a is from a to b, the top function minus the bottom function, dx. And if you look back at our example above here, our top function is going to be y squared plus 1, because that one is on top or above our y equals x. Okay, so that's why we chose x squared plus 1 subtracted by x, because our parabola is above our linear graph. So here are some steps to find the area between the curves. You should draw the picture and shade the area that you want. We can draw an arbitrary rectangular strip representing one rectangle in the Riemann sum approximation, and then find an expression for the area of that strip or slice. This part is optional. You don't have to do it. If it helps you think about the question a bit better, then you can go ahead and do it, but it's not a necessity in order to find the area between two curves. Then you want to integrate the area expression, which you need to find for our, if you're using this method, it's going to be a single slice or just for the entire thing over the interval to get the area between the curves. The examples I'm going to show you are going to cut out steps 2 and 3, and we're just going to look for the area of the entire thing. But we're still going to draw the picture, a rough graph of it. So we have f of x is equal to e to the x. We know we're going to pass through 1 on our y-axis. It's an increasing function that looks like this. I don't need to draw anything more between 0 to 1. Those are our bounds. And then I also want to draw our linear graph of x. So I know there's a point at 1, 1. It looks something like this. And because we're stopping at x equals 1, I'm going to close it off over here. And our function is going to be bounded between 0 to 1. So this is the area that we are looking at. So our area is going to be from our bounds of 0 to 1. We look at the top function. Looks like that's going to be e to the x, and y equals x is our bottom function. So remember, it'll be top minus bottom for your functions. The top one's e to the x, the bottom one's x. And that's how we set up to find the area between those two curves. We're going to go ahead and integrate. So the integral, or antiderivative of e to the x, e to the x. And for x, that's 1/2 x squared. I'm going to evaluate this from 0 to 1. So we can get e minus 1/2 minus e to the 0, which is 1, minus 0. So this will be e minus 3 over 2, which is about 1.218, and that's our final answer. Example 3, same sort of thing. We want to draw it out, and we're going to see what our bounds are going to be when we draw it, because we aren't given the bounds. But let's try to see what this is going to look like. So x squared is going to look something like this. And then 2x minus x squared, we're going to have to complete the square so we know what our big vertex is going to be at. So this will be negative x squared minus 2x we're going to divide this 2 by 2, and then that's going to be 1. And then when squaring that, we still get 1. And we'll just subtract it out as well. Going to factor, taking out this -1 and multiplying by the -1 in the front to reverse our factoring, we get a +1. So we have our vertex at 1, 1. And it's going to be an upside down graph. Okay, so the area between those two curves then is going to be this region right here. So that means our bounds are going to be from 0 to 1. Our top function looks like it is going to be this one here, which is y equals 2x minus x squared. And then our bottom one is just going to be x squared. So our top function is 2x minus x squared minus x squared dx. And then we're going to simplify this. So this is going to be 2x minus 2x squared dx, which is x squared minus 2 over 3 x to the power of 3. I'm going to integrate this from 0 to 1. So that's 1 minus 2 over 3, and then minus 0, which is 1 over 3, and that's our final answer there. To use our calculator, make sure you have your graphing calculator to do this question. First of all, we need to figure out which one is the top function. So we can graph this into our graphing calculator, and that's your first step. And you're doing this to determine which function is on top. Then afterwards, with that graph, find the points of intersection. So once you graph those two graphs, you're going to use your graphing calculator to find the points of intersection. And they should be x equals 0 and x equals 1.181. Then these are going to be your bounds. So we can set up our equation from 0 to 1.181 is going to be f of x minus g of x, because if you graph from your calculator, you're going to see that f of x is above the g of x. So this is the top function minus your bottom function. And you just let the calculator do the work to get the final answer. It's going to be 0.785. Okay, another example. I'm going to graph this first. We have y equals the root of x. We don't know what our bounds are, so we will have to find it. Okay, so that's y equals the root of x. The other one is going to be x minus 2. So minus 2 is your y-intercept, and then our slope is just 1 up over 1. Something like that. So if I'm looking about the area between the curve, it's going to be this region here. And take a note, it says y is equal to 0. So this is another bound that we have, that we're not going to go below the x-axis. So this is the region we're looking for. With this specific question, it's not as easy as you think that we could just do the root of x minus 2, because then we're going to consider this region here, and we don't want to because our area has to be bounded by all of these. So I have to cut actually this into two regions, because the bottom function for our first area is bounded by root of x and also y equals 0. So this is, we can call this area 1, and it's bounded by the root of x and 0. For area 2, this one is bounded by x minus 2 and the root of x. So we're going to calculate it into two portions, which is going to be area 1 plus area 2. Now focusing on area 1, we're going to go from 0 to this place over here, which is 2. Our top function is the root of x. Our bottom function is 0. Okay, and then for area 2, we're bounded from 2 to 4. Your top function is the root of x, and then your bottom function is x minus 2. Don't forget your brackets, it's pretty important because it's negative, will distribute. Now we're going to simplify this a bit. And then we're going to go ahead and then integrate each. So once you do that, your final answer will be 10 over 3. The other way you can calculate the area is to change your functions in terms of y. So the ones we just did, all of our functions were in terms of x, and we would do top minus bottom. Sometimes with the functions given to you, it's actually easier for you to change in terms of y, so you can do right minus left instead. So we're going to see several examples of how this could occur. The first thing you're going to do is graph. So it's already written in terms of y for us. And if you want to know what this actually looks like, this is going to be the root of x is equal to y if you take the square root of both sides. So I'm going to draw the root of x. Looks something like that. And then if you want to know what this looks like, you just rearrange and solve for y. And that would be x minus 2, so it's the same graph as before, as you can see. Something like that. And y equals 0. So here's the same graph as before. So here in this example, we did two sections. If we use our functions in terms of y, we only need to do this once. we're going to use our right function minus our left function. So it's going to be the smallest y value to the greatest y value that were bounded between those two curves. And then you do your right function minus the left function. And because we're in terms of y, it'll be dy. So if we look at our smallest y value, because we're bounded by y equals 0, this is your smallest y value then. Your highest y value is going to be at 2. So those are our bounds. The function that is to the right is going to be this one here. And that one is your y plus 2 function. Then your left one is going to be your y squared. Okay, so your right is y plus 2, your right is y squared, and dy, and then we're going to integrate this. And you should still get the same answer. But it's just different methods. So this is a scenario where putting your functions in terms of y would actually be quicker and easier. Okay, for this next one, we are going to use our calculator to help us. We want to graph y equals x cubed, and we also want to graph x equals y squared minus 2. And your graphing calculator probably likes this better in terms of x, so I'm going to rearrange and solve for y here. And that is what you're going to graph in your graphing calculator instead of x equals y squared minus 2. We just move the 2 to the other side and then square root both sides to solve for y. Now if you graph this in your graphing calculator, you're going to get something like this. That's your y equals x squared graph. And then we also want to graph our root of x plus 2. And we did take the square root of it, so we need to consider both sides of it, the plus and minus of it. If I just think about the plus side, I'm going to have a point at negative 2, 0. And then my next point can be at, if we set x or 0 for x, I'm going to get the root of 2, which is about 1 point something. So it's going to look something like this. And the same thing's going to happen on the other side. It's like a parabola on its side. Okay, so the area between these two curves is this region over here. Again, you could just use your calculator to help you graph those two functions. And we're also going to use our calculator to find the intersection points. So we have an intersection point here and an intersection point here. And when we use our calculator, we find that this is going to be 1.215, 1.793, and the bottom one is going to be at negative 1,1. Okay. So in this case, we are going to use terms of y because we have a most right and a most left function. And then we also have the lowest y value and the highest y value. If you did it in terms of x, you can, but there's going to be multiple areas you do need to consider while you're doing this. So we're going to integrate from our lowest y value, which is -1, to our highest y value, which is 1.793. Our most right function is going to be y equals x cubed, but in terms of y, then I have to rewrite this as x equals to the cube root of y. So our most right function is cube root of y minus y squared minus 2 in brackets dy. And then if you want to do a calculation here, you can probably use your graphing calculator, knowing that we have a decimal as part of our bounds. So this will be 4.215. Lastly, for example 8, we've been given the function f, which is this one over here, and the line y equals 4. So the vertical line sum k divides R into two regions with equal areas. But we want to write but do not solve an equation involving the integral expressions whose solution gives the value of k. So we have area 1 and area 2 to consider. And we don't know what the value of k is. We know this line is y equals 4, and we also know what our f of x equation is. So if we just focus on area 1, we have a top function and a bottom function. So that'd be from 0 to some line k as our bounds. Our top function is 4. Our bottom function is f of x, which is x to the power 4 minus 2.3x cubed plus 4 dx. Now let's focus on area 2. Our bounds are going to be from k, and we need to figure what this is right now. We need to figure out the intersection point over here to figure out the x value for that. You can do that in the graphing calculator, and we're going to get 2.34 here. So you would graph f of x and y equals 4 together, and then find that intersection point coordinates. Okay, so that x value is going to be 2.3 then. Our top function is 4. Our bottom function is f of x, which is x to the power 4 minus 2.3 x cubed plus 4. So if we want to find k, all we have to do is equate area 1 and area 2, because we know that they are the same. They have equal areas. So all I have to do is rewrite my integrals in for a1 and a2. And then we use this to solve for k. We just integrate each integral and solve for k that way.